Hello, today we're going to start with an introduction for our unit on reactions. Let's do a quick review of the different types of matter. So matter can be kind of broken down into two main categories: substances, substances and mixtures. And then substances can be classified further as elements and compounds. Now, compounds will have two or more elements chemically combined. Elements are just, the pure element in its elemental form. Mixtures can be broken down further into two types. We have heterogeneous and homogeneous. Heterogeneous, you'll typically see like different layers or like easily distinguishable separate parts. And heterogeneous, if you take a sample from any portion of your mixture, you might get a different composition, so a different ratio of different things. But in a homogeneous mixture, it's completely evenly mixed. If you take a sample from any part of the mixture, it will be the same as any other part of the mixture. And solutions are considered types of homogeneous mixtures. Okay, so this should be all review, but just the difference between substances and mixtures there. Okay, let's talk for a minute about chemical and physical changes. In a physical change, the types of compounds or elements present do not change, but you might see things like phase changes. So you're changing the state of matter. So like you take solid water, ice, and you melt it into liquid water, it's still H2O, so you're clear that it's a physical change. And then going from a liquid to a gas, boiling the water off, again, still water, so that is a physical change. Make sure that you know all of your phase changes. Gas to solid is melting, solid to liquid is melting, liquid to gas is vaporization. In the reverse, gas to liquid is condensation, liquid to solid is freezing. Now, if you jump directly from a solid to a gas, that's sublimation, and from a gas to a solid is deposition. Another type of physical change would be separating mixtures. And we've talked about that earlier, separation of mixtures. There are a few big types of separations that you should know, like filtration, distillation, chromatography. But again, those are physical changes because you're not changing what's present, you're just separating the components. Chemical changes, on the other hand, will have to result in a change in the type of substance. So the bonds could break and form new bonds, but in any case, the bonds have to change in a chemical reaction. The specific elements are not changing unless you have a nuclear reaction, but the compounds could change, how the elements are bound together. Now, we use a few clues to tell whether or not a chemical reaction is occurring. And I call them clues because they're not perfect, and we'll talk about why, but there's a handful of them. If you form a precipitate is the solid that forms as the result of a chemical reaction. So if you see a solid being formed, it's probably a chemical reaction. If there's a color change, if the reaction produces light, so if it starts to glow, if there's a change in temperature, whether it's producing heat or absorbing heat, you'll see the temperature go up or down. And then another one would be if it's bubbling. And if it's bubbling, that means it's producing a gas. Now, again, let's call these clues because if, for example, if you just add like a dye to another substance, that's not necessarily a chemical reaction. That's just the dye changing the color. Another example would be bubbling. If you put water on the stove and start to boil it, it bubbles. But that's not a chemical reaction, that's a physical change. So like I said, these are just kind of clues. They're good indicators, but they're not perfect. Okay, I'm going to give you a brief introduction to some of the types of chemical reactions we're going to look at, and kind of the pattern of how they're reacting. We'll get more specific with this later on. But the first one I want to talk about is combination or synthesis. synthesis. And that's where if you have two separate things, and they combine together into one product, that's synthesis or combination. Decomposition reactions is when you have one thing and it's splitting apart into its component elements. That's decomposition. Let's see, single replacement. Single replacement is where you have an element reacting with a compound, and the element is switching places with one of the elements in the compound. So you'll wind up with something like this. So you can see how it's changing its location. That's single replacement. The next one is double replacement. Double replacement is when you're reacting two ionic compounds and the metals swap partners. So you wind up with something like this. And I'm just using generic letters so you can see the pattern. And the last one is combustion. Now if you have combustion, I'm going to give you two kind of formats here. If you have combustion of a metal, combustion is always reacting with oxygen gas. If it's reacting with a metal, it's going to combine. But if it's reacting with a hydrocarbon, it forms carbon dioxide gas and water vapor. Typically water vapor. It could be water liquid depending on the temperature, but it will produce carbon dioxide and water. So this one's kind of a special case. But yeah, so that's how kind of we can see the patterns of reactions through this. Now, double replacement is going to be things like acid-base neutralization reactions, which we will talk about later, or precipitation reactions, and that would be where one of these might be a solid, which we're going to talk about in the next section. The other ones, synthesis, decomp, single replacement, and combustion, all four of those are types of redox reactions, oxidation reduction reactions. And again, we're going to talk about that in a later section, but this is a nice little intro for these patterns. Okay, so when you're doing reactions with transition metals, you need to be very careful of their charge. Transition metals can have different charges depending on their oxidation state. So the transition metals typically are in the D block on the periodic table, but you should also know that lead and tin also act like transition metals, even though they're not in the D block. And then you should also know that zinc always forms a 2+ charge, even though it is in the D block. So you don't need to consider zinc a transition metal. Now, transition metals will typically have in the name, it will have their charge. So if you have like iron 3 chloride, the 3 indicates the charge on the iron. So you know that iron would have a charge of +3 and chlorine would have a charge of -1. So you need 3 of them to cancel that out. But you can also have iron 2 chloride. And so in this case, the iron would have a charge of 2+, chlorine's always -1, so you'd need 2 of those to balance out the iron. So the charge on the transition metal is going to affect the formula of your compound. Now typically, if we have a double replacement reaction, that charge will not change. So if the iron has a +3 charge on the reactant side, it will have a +3 charge on the product side, which is nice. So if you can figure out one side, then you can figure out the other side of the reaction. They might not give you the name. They might just give you the formula of the compound, and then you'd have to figure it out. So they could give you something like PbO2. All right. If they just give you the formula, you need to use the charge on the non-metal to figure out the charge on the metal. So in this case, oxygen has a charge of 2-, but there's 2 of them, so the lead must be +4 in order to balance out those 2 negative charges. And if it's a double replacement reaction, you know it's going to be the same charge on both sides, so +4 on the reactants and the product side. So be really careful with transition metals there. If it's not a double replacement reaction, they'll have to give you more information so you know what's happening with the charge. So sometimes they'll say it's forming a solid. So if it's forming solid iron, you know that its charge is 0 because it's a solid, it's all by itself. or they'll actually just tell you like the compound that is being formed. So they'll give you the information that way. You should also be careful with reactions that have polyatomic ions. Polyatomic ions have multiple atoms that make up the ion. There's a few that I recommend that you kind of memorize. And so one of them is phosphate. Phosphate is PO4 3 negative. So anytime you see PO4, it has a charge of -3. Sulfate is SO4 2 negative. Carbonate is CO3 2 negative. Nitrate is NO3 1 negative. Acetate is C2H3O2 negative. Chlorate is ClO3 negative. Let's see, a hydroxide is OH negative, and then ammonium is NH4 plus. So those are the ones that I recommend that you kind of remember because you might need to use their charge to figure out the formula of compounds that are being formed. So like, I don't know if I have sodium. Sodium always forms a +1 charge because it's a group 1 metal. So if I'm forming a compound with sulfate, I need to know that it has a -2 charge, so that way the formula of the compound is Na2SO4. So that's how polyatomic ions will affect it. Okay, so let's kind of put all of this together. Let's say we have a reaction, FeBr3 reacts with CiSO4, right? And I want to predict the products. I know this is going to be a double replacement reaction because it's got 2 ionic compounds, so the metals are going to switch partners. The calcium will wind up with bromine, and the iron will wind up with sulfate. You need to pay attention to their charges, though. Calcium will wind up with bromine. And calcium's a group 2 metal, has a 2+ charge. Bromine's a halogen, will have a -1 charge. So I need 2 bromines to make that ionic compound accurate. The other one would be the iron with the sulfate. Well, if you remember your polyatomic ions, you know the sulfate is 2 negative. You could also use the calcium. Calcium's always 2 positive to help you remember that the sulfate is 2 minus. Iron, in this case, must be +3 because bromine is -1 and there's 3 of them, so the iron is +3. It's still going to be +3 on my product side. So Fe has a 3+ charge, SO4 has a 2- charge. The only way to get those ions to balance out perfectly is if I do Fe2, SO4 3, and now the ionic compound is balanced for those charges. And so that's kind of how you put that together. You need to determine the type of reaction to figure out where the elements are going, and if it's creating a new product, a new compound, then you need to use the charges to make sure that that ionic compound has the correct formula. The other thing that you want to kind of be aware of is the diatomic elements. So let's say you have a reaction like sodium chloride reacts with F2, just fluorine gas. All right, fluorine is a nonmetal. It's going to swap with the nonmetal in the compound. So sodium, which is +1, will react with fluorine, which is -1, so that balances out perfectly. Now the chlorine will wind up by itself, but you need to know that there are 7 diatomic elements, and that they are Br, I, N, Cl, H, O, and F. So we use Brinkelhoff, and all of those, when they are by themselves, they're actually in a partner. They're diatomic. So I have chlorine by itself, it really needs to be Cl2 because it's one of those 7 diatomic elements. Then of course after this you would balance these reactions, but I'm going to leave it here for this particular slide. Just know that once you figure out the products, then you should balance. All right, and the last part for this section is we're going to talk about gas evolving reactions. Gas evolving or gas producing reactions, they produce particular gases. Now, there's two types that you need to kind of recognize. If your reaction produces H2CO3, or if your reaction produces H2SO3. Those compounds are very unstable. What happens is they immediately break down into H2O and CO2. And for the sulfur one, you'd have H2O and SO2. So when you're writing the products, instead of writing these compounds, you're going to write water and this. And so these are gases that are being formed. Water is typically a liquid, as long as you're at room temperature. And so they're producing gases, so I would call them gas-evolving reactions. So you just want to remember, anytime you see H2CO3, break it down into H2O and CO2. Anytime you see H2SO3, break it down into H2O and SO2.